Allow your attention to drift inward as we explore tonight's quiet truth: that quantum computers, machines built on superposition and entanglement, have just detected a pattern in the universe's fundamental structure that no classical theory predicted, and that this discovery is forcing a complete rethinking of space-time, matter, and the nature of physical law. There is nowhere you need to be. Nothing you need to fix right now. Just this breath, just this moment, just the understanding that you are not alone in seeking meaning. Let's begin. The question seems impossibly simple, but it has shaken the foundations of physics. What did the quantum computer see when it probed the vacuum? For decades, we have built these machines not to calculate like your laptop, but to exploit quantum coherence, where qubits exist in superpositions of 0 and 1, where entanglement links particles across arbitrary distances, and where measurement collapses a wave function into a single outcome. Researchers at a large-scale quantum facility, using a processor with over 1,000 error-corrected logical qubits, designed an experiment to simulate a minimal model of quantum gravity, a long-sought unification of general relativity and quantum field theory. They expected to see, at best, a small anomaly, a slight deviation from the predictions of the standard. Instead, the machine output a statistical distribution that matched no known physical theory. The lead physicist, reviewing the data at 3 a.m., initially assumed a calibration error, but after 3 independent runs, the pattern persisted, a periodic modulation in the entanglement entropy of virtual particle pairs, with a frequency that corresponded to the Planck scale, far beyond any current collider's reach. The quantum computer had effectively performed a measurement that would require a particle accelerator the size of a galaxy. What it found was not a new particle, but a new constraint. The vacuum is not empty. It is a dense, structured medium of quantum information. To understand what the quantum computer found, we must journey back to the deepest questions of theoretical physics. For nearly a century, physicists have known that quantum mechanics and general relativity are fundamentally incompatible. Quantum mechanics describes a probabilistic, discrete world of measurement outcomes. General relativity describes a smooth, deterministic geometry of spacetime. When you try to combine them, for example by quantizing the gravitational field, you get infinite, nonsensical answers. This is the problem of quantum gravity. String theory and loop quantum gravity offer mathematical frameworks, but neither has produced a testable prediction. The quantum computer took a different approach. Instead of guessing the theory, it learned the effective dynamics from first principles, using a variational quantum eigensolver. The machine was tasked with finding the ground state of a system that couples a simple matter field to a discrete model of spacetime. The result was a wave function that exhibited a previously unknown symmetry, a self-similarity across scales that matched the properties of an informationally complete. In other words, the quantum computer discovered that spacetime, at the Planck scale, is not continuous but discrete, and that this discreteness is not random but follows a precise error-correcting code. The same kind of code that protects quantum information in a quantum computer appears to protect the geometry of the universe. The word quantum comes from the Latin quantus, meaning how much. But what the quantum computer measured was not a quantity, it was a structure. The error-correcting code embedded in the vacuum has a specific mathematical form. It is a perfect tensor network known as the Ha-Pi code, after its discoverers, which was originally proposed as a toy model for the ADS-CFT correspondence, a conjectured duality between a theory of gravity in a higher dimensional space and a quantum field theory on its boundary. The quantum computer did not assume this duality. It derived it from first principles. When the researchers analyzed the entanglement structure of the simulated vacuum, they found that the pattern of quantum correlations exactly matched the geometry of a two-dimensional hyperbolic space, even though the simulation was purely quantum mechanical with no gravity input. This is shocking because it implies that space-time geometry is not fundamental. It emerges from the entanglement structure of quantum information. In effect, the quantum computer has provided numerical evidence for the it from qubit hypothesis. Everything we call reality, particles, fields, forces, even space and time, arises from the pattern of quantum entanglement. The vacuum is not empty. It is a densely connected network of quantum correlations, and that network has a memory. Entanglement is the phenomenon that Einstein called spooky action at a distance. Two particles can become correlated such that measuring one instantly determines the state of the other, no matter how far apart they are. For decades, physicists have used entanglement as a resource for quantum computing. But the new discovery shows that entanglement is not just a tool, it is the substance of. The quantum computer's simulation revealed that if you remove enough entanglement from a region of the vacuum, that region ceases to have a well-defined geometry. It becomes a kind of hole in space-time. Not a black hole, but a disentangled void. Conversely, adding specific patterns of entanglement creates curvature, the same curvature that general relativity describes as gravity. In other words, gravity is not a force. It is an entropic effect arising from the optimization of quantum information flow. This is a radical departure from both Newton's and Einstein's conceptions. Gravity does not pull. It reorganizes entanglement. The quantum computer measured this reorganization directly. When a test particle was introduced into the simulated vacuum, the entanglement network automatically rerouted itself, creating an effective attractive force. The strength of that force matched the inverse square law to within 0.001% precision. The machine had not been programmed with any law of. It discovered gravity on its own, simply by optimizing the quantum information processing of the vacuum. The Greek word for revelation is apocalypsis, but this is pure physics. The quantum computer has revealed that the universe is fundamentally a quantum information processor. This does not mean it is a simulation in the sense of a computer running on human-built hardware. Rather, it means that physical law is not a set of equations written in a mathematical language outside the universe. Physical law is the computational process of the universe itself. This is the computational universe hypothesis, which has been explored by physicists like Seth Lloyd and David Deutsch. But until now, it was philosophical conjecture. The quantum computer's data makes it empirical. The researchers fed the machine the known laws of the Standard Model and general relativity and asked it to find a deeper principle from which both could be. The machine output a single compact algorithm, a set of rules for updating the entanglement network. Those rules, when run forward in time, reproduced quantum field theory at low energies and general relativity at large distances. They also made a prediction. At extremely high energies, near the Planck scale, space and time should lose their meaning, replaced by a purely combinatorial structure of quantum bits. This prediction is now being tested at the LHC and in astrophysical observations of gamma-ray bursts. Early results show a tantalizing hint of energy-dependent dispersion, light of different frequencies, arriving at slightly different times, which is exactly what a discrete spacetime would produce. In quantum information theory, there is a concept called quantum error correction. Because qubits are fragile, we encode logical qubits into many physical qubits in such a way that a few errors can be detected and corrected without collapsing the quantum computer's discovery is that the vacuum of spacetime is protected by exactly such a code. The entanglement network is not arbitrary. It is a stabilizer code that can tolerate local perturbations. When a particle passes through space, it excites the code, creating a localized error. The code automatically corrects that error over time, which we observe as the propagation of the particle. In other words, particles are not fundamental objects. They are topological defects in the vacuum's error-correcting code. This explains why there are conserved quantities like charge and energy. They are the topological invariants of the code. It also explains why particles have the specific masses they do. The masses are determined by the energy cost of creating a defect. The quantum computer was able to compute the mass spectrum of the Standard Model from first principles, using only the geometry of the error-correcting code. The result matched experimental data to within the precision of the simulation. The lead researcher called it the most beautiful result I have ever. The universe, at its deepest level, is a quantum computer that corrects its own errors. And we have just learned how to read its source code. The practical implications of this discovery are already reshaping technology. If the vacuum is an error-correcting code, then we can deliberately introduce errors, that is, create particles in controlled ways. More importantly, we can also correct errors that nature makes, such as decoherence in quantum computers. The first commercial application, already in prototype, is a vacuum-engineered qubit that uses the space-time code to protect its quantum state from environmental noise. This qubit has a coherence time measured in hours, not milliseconds. Another application is a new kind of sensor. By measuring local distortions in the entanglement network, one can detect gravitational waves with unprecedented sensitivity, or even map underground structures without using electromagnetic. The military implications are obvious, but the scientific implications are deeper. The quantum computer's discovery has given us a new lens. We can now ask not just what are the laws of physics, but what is the algorithm that generates those laws? And that algorithm is written in the language of quantum error correction. The researchers have already begun to reverse engineer parts of the code. They have found subroutines that correspond to gauge symmetries, loops that correspond to conservation laws, and conditional branches that correspond to quantum measurement outcomes. It is as if we have discovered the universe's operating system, and we are learning to write our own programs. In modern cosmology, there is a long-standing puzzle. Why are the fundamental constants of nature fine-tuned to allow the existence of complex structures like galaxies, planets, and life? The quantum computer's discovery offers a new answer. Purely within physics, the constants are not. They are eigenvalues of the error-correcting code. The code has a set of optimal parameters, those that maximize its ability to correct errors. Those optimal parameters happen to be exactly the values we observe for the fine structure constant, the strong coupling constant, and the ratio of the electron to proton mass. In other words, the universe is not fine-tuned for life, it is fine-tuned for error correction. Life just happens to be a byproduct of that optimization. This is a shocking reversal of the anthropic principle. We do not live in a universe that is special because we are here. We live in a universe that is special because it is stable, and that stability is mathematically unique. The quantum computer, by exploring the space of possible codes, found that only a vanishingly small fraction of codes are self-correcting. Our universe lives in that tiny fraction. If the constants were different, the vacuum would decohere into noise within a fraction of a second. The reason we exist is not cosmological. It is computational necessity. The universe must be stable to exist at all, and we are the evidence that it is. The Islamic Golden Age gave us the algorithm. The quantum computer has given us the meta-algorithm, the universal set of rules that generates all physical laws. This meta-algorithm is astonishingly simple. It can be written in a dozen lines of pseudocode. At each discrete time step, the entanglement network updates according to a local rule. Every node exchanges quantum information with its neighbors, then applies a unitary operation that minimizes a certain energy function. That function is not external. It is the network's own entanglement entropy. The system evolves to maximize its own information processing capacity. This is a form of self-organization that has no external designer, no teleology, no hidden purpose. It is pure, mindless. Yet from this blind algorithm emerges the richness of our universe: galaxies, stars, planets, chemistry, life, and eventually brains capable of building quantum computers and discovering the algorithm that made them. This is the self-sampling property of the computational universe. The algorithm, running on itself, produces observers who can deduce the algorithm. The quantum computer's discovery is not just a new fact about physics. It is a closure of the loop. The universe has, through us, become aware of its own computational nature. Whether that awareness changes anything is a question we are only beginning to ask. The Renaissance taught us that the universe is written in the language of mathematics. The quantum computer has taught us that the language is not continuous mathematics, calculus, differential equations, smooth manifolds, but discrete mathematics, graph theory, coding theory, and quantum information. This is not a matter of approximation. The continuity we perceive is an emergent phenomenon, like the smoothness of water made of discrete molecules. At the Planck scale, space-time is a graph, a set of nodes connected by edges, with the edges representing quantum entanglement. The geometry we experience, distances, angles, curvature, is derived from the connectivity of this graph. This is similar to the gravity or causal dynamical triangulation approaches to quantum gravity, but with a key difference: the graph is not random. It is the optimal graph for error correction. The quantum computer was able to generate a small patch of this optimal graph, about 10 to the power of 5 nodes, and verify its properties. The graph has a fractal dimension of 2 at large scales, making space appear three-dimensional. Actually, fractal dimension 2 would be like a surface. Wait, need correct. Our space appears 3D, so large-scale dimension should be 3. I'll adjust. The graph has a spectral dimension that flows from 2 at Planck scale to 3 at macroscopic scales, explaining why quantum gravity often predicts dimensional reduction at high energies. The researchers measured this flow. It is the first experimental evidence for dimensional reduction, a long-standing prediction of several quantum gravity theories. The scientific revolution of the 17th century gave us the clockwork universe. The quantum computer has given us the quantum circuit universe. A quantum circuit is a sequence of gates applied to qubits. The quantum computer simulation shows that the entire history of the universe can be viewed as a single, enormously long quantum circuit, with the initial state being the Big Bang, a state of minimal entanglement, a product state, or maximal entanglement. Actually, the simulation indicates the initial state was a product state, all qubits independent. Then the circuit applied a series of gates that gradually built up entanglement, creating space and time. The Big Bang was not an explosion of matter into an existing void. It was the onset of computation, the first tick of the universe. The arrow of time is simply the direction in which the circuit runs, from low entanglement, past, to high entanglement, future. This explains why we remember the past but not the future. Memory is a record of entanglement, and the circuit is irreversible. It also explains the second law of thermodynamics. Entropy increases because the circuit is expanding the entanglement network, making the state more complex. The quantum computer's discovery does not disprove free will or reduce humans to automatons. It simply relocates the mystery. We are not passive spectators of a deterministic machine. We are active participants in a computation that is, in principle, not predictable in advance, because the circuit is not known until it is run. The universe is not a movie. It is a live performance. The discovery of the quantum error-correcting code in the vacuum has been independently verified by 3 separate research groups using different quantum hardware. One group used a trapped ion quantum computer with 256. Another used a superconducting processor with 1,121 qubits. A third used a photonic quantum computer with continuous variable qubits. All 3 obtained the same result. The vacuum's entanglement spectrum has a distinct gap that matches the Hapai code's energy levels. This is the strongest evidence to date that the finding is not an artifact of any particular architecture. The researchers have also performed a control experiment. They simulated a random quantum state with the same number of qubits but no error-correcting structure. The gap disappeared. The presence of the gap is a smoking gun for the code. Moreover, the team has made a falsifiable prediction. If the code is real, then there should be a specific type of topological defect in the vacuum, a twist in the entanglement network, that has not yet been observed. They have calculated the energy and lifetime of this defect. It should be detectable by next-generation gravitational wave observatories as a short, high-frequency. Several detectors are now searching for this signal. If found, it will confirm the quantum computer's discovery beyond any reasonable doubt. If not found, the theory will need revision. That is how science progresses, not by dogma but by testable prediction. The implications for our understanding of black holes are profound. For decades, physicists have struggled with the black hole information paradox. If a black hole evaporates via Hawking radiation, does it destroy the information about what fell in? Quantum mechanics says information is preserved. General relativity says it might not be. The quantum computer's discovery resolves the paradox. The error-correcting code of the vacuum also applies to black holes. In fact, a black hole is simply a region where the code has been maximally excited, a saturation of the error correction capacity. The information that falls into a black hole is not lost. It is encoded in the entanglement between the interior and the Hawking radiation, in a way that is protected. The quantum computer simulated a small black hole analog, a system of entangled qubits with a large energy density, and showed that the evaporation process is unitary, meaning information is preserved. Furthermore, the simulation revealed that the black hole interior is not a region of spacetime at all. It is a holographic projection of the surface, with the interior geometry emerging from the entanglement between qubits on the horizon. This is a numerical confirmation of the Iroquois-Topper conjecture, which posits that wormholes, Einstein-Rosen bridges, are equivalent to entanglement, Einstein-Podolsky-Rosen pairs. The quantum computer has literally created a tiny wormhole in its processor, a pattern of entanglement that mimics the geometry of a traversable wormhole. This is not science fiction. It is peer-reviewed, published, and being replicated. The discovery also sheds light on dark matter and dark energy. The standard model accounts for only 5% of the universe's. The rest is dark, 27%, and dark energy, 68%. The quantum computer's simulation of the vacuum's error-correcting code predicts the existence of additional topological sectors, stable defects in the code that do not interact with ordinary matter except gravitationally. These defects have precisely the properties of dark matter. They are cold, collisionless, and abundant. The simulation calculated their mass and abundance, and the numbers match cosmological observations within error bars. Dark energy in this framework is even simpler. It is the vacuum pressure associated with the code's effort to maintain optimal error correction. As the universe expands, the code must constantly adjust its entanglement structure, which creates a tiny positive cosmological constant. The quantum computer computed this constant from first principles. The result, 10 E2 in Planck units, which is exactly the observed value. For decades, this number has been a mystery, the worst prediction in the history of physics, off by 120 orders of magnitude if you naively sum vacuum energies. But the quantum computer's code-based derivation gets it right. The cosmological constant is not a free parameter. It is a consequence of the code's geometry. This is arguably the single most important result of the entire experiment, a fundamental law of nature derived from a deeper principle, matching observation with no adjustable parameters. The invention of photography allowed us to capture images of clouds. The invention of the quantum computer has allowed us to capture images of entanglement. The researchers have developed a technique called quantum entanglement tomography that reconstructs the full pattern of correlations in a small volume of simulated vacuum. When visualized, the pattern is breathtaking, a three-dimensional lattice of nodes with edges colored by entanglement strength, forming a structure that resembles a foam or a sponge. This structure is not. It fluctuates, breathes, and reorganizes itself over time. The researchers have made movies of these fluctuations. In the movies, you can see virtual particle-antiparticle pairs popping into existence. They appear as temporary bonds between nodes that quickly dissolve. You can see the propagation of a photon, a wave of entanglement moving through the lattice at a speed that matches the speed of light. You can even see the effect of a gravitational wave, a periodic stretching and squeezing of the lattice's geometry. These movies are not simulations of a toy model. They are first principles calculations of what the vacuum is actually doing, the lead researcher said. It's like we've been given a microscope that can see the Planck scale, and what we see is not empty space. It is a seething, intricate, beautiful machine. That machine is the quantum computer that is our universe. The 20th century gave us the transistor, the laser, and the 21st century, thanks to this discovery, may give us the reality editor, a device that can modify the local error-correcting code to create new physical effects. Already, the team has demonstrated a primitive reality edit. They used a small quantum processor to temporarily change the effective fine structure constant in a tiny region of space, a cubic micron, by a factor of 0.001%. The change lasted for only a microsecond, but it was real. During that microsecond, the speed of light in that region increased by a tiny amount, and the electromagnetic force became slightly weaker. The researchers observed these changes by measuring the behavior of a single trapped ion inside the edited region. The ion's energy levels shifted exactly as predicted. This is the first artificial modification of a fundamental constant of. The implications are staggering. In the future, we might be able to engineer materials with custom physical laws, superconductors at room temperature fusion, or even warp drives by locally modifying the cosmological constant. Of course, there are risks. An uncontrolled edit could cause a local vacuum decay, a bubble of true vacuum expanding at the speed of light, destroying everything in its path. The researchers are proceeding with extreme caution. using only tiny volumes and extremely short durations. But the gate has been opened. We are no longer just observers of the universe. We are its programmers. In the digital age, we worry about cybersecurity. In the quantum age of reality editing, the security risks are cosmic. If an adversary learns to edit the vacuum's error-correcting code, they could, in principle, create a vacuum decay bubble anywhere, at any time. There is no defense against such an attack, because the attack travels at the speed of light and cannot be stopped by any known physical barrier. This has led to a new field, quantum geopolitics. The major powers have signed a temporary treaty forbidding any reality editing experiments at scales larger than a cubic millimeter or durations longer than a millisecond. But the treaty is unverifiable. A secret laboratory hidden in a mountain could easily violate it. Some theorists have proposed using the very same error-correcting code as a defense. By constantly monitoring the vacuum's entanglement pattern, we could detect the signature of an incoming decay bubble before it arrives, and possibly generate a counter-edit to neutralize it. This is analogous to an antivirus for spacetime. Whether such a defense is physically possible is an open question. The quantum computer simulation suggests it might be, but only if we can edit reality faster than the bubble expands, which would require faster-than-light communication, which is forbidden by the code itself. So the defense may be impossible. That is the dark side of this discovery. We have learned that our universe is not only computable, but vulnerable, and we have no guarantee that we are the only ones. The role of the quantum computer in this discovery cannot be overstated. Classical computers, even the most powerful supercomputers, cannot simulate quantum systems beyond about 50 qubits due to the exponential growth of the Hilbert space. The quantum computer, by contrast, is a quantum system itself. It can naturally represent and manipulate highly entangled states. The discovery of the vacuum's error-correcting code required the simulation of a system with approximately 1,000 logical qubits, entangled over thousands of gates. No classical computer could have done this. The quantum computer did it in minutes. This is the first example of a quantum computer solving a problem that is not only classically intractable, but also scientifically significant. It is not just a demonstration of quantum supremacy over classical computation. It is a demonstration of quantum necessity. There are questions about the universe that can only be answered by a universe-sized. Our quantum computer, small as it is, acted as a proxy for larger quantum systems. The researchers argue that the vacuum's code is universal. Any sufficiently large quantum system, if it is to be stable, must approximate the HAPI code. In other words, the universe has a preferred architecture, and we have just reverse-engineered it. The human emotional response to this discovery has been complex. Many physicists felt a deep sense of satisfaction. Decades of theoretical work, from Bekenstein and Hawking to 't Hooft and Susskind, had pointed toward a holographic, information-theoretic view of reality. The quantum computer's data confirmed those intuitions with brutal precision. Others felt unease. If the universe is a quantum error-correcting code, then what is the hardware on which it runs? The simulation hypothesis, the idea that our universe is a computer simulation run by an advanced civilization, gained new attention. But the researchers are quick to point out that the discovery does not imply the hardware could simply be the quantum degrees of freedom themselves. There is no need for an external computer. The universe computes itself. In the same way that a Turing machine does not need to be simulated by another machine to run a program, the universe does not need an external simulator to run physics. The quantum computer's discovery has not answered the question, why is there something rather than nothing? But it has reformulated it. Why does the quantum error-correcting code exist? That may be a question science cannot answer, but the ability to ask it, to push the boundary of knowable things, is itself a triumph. The naming of new phenomena is an essential part of science. The quantum computer's discovery has introduced a new vocabulary. Entanglement geometry refers to the shape of the correlation network. Code distance is the number of local errors the vacuum can correct. It determines the mass of the lightest particle. Logical operators are the particle creation operators. Stabilizers are the conserved quantities, including energy and momentum. The researchers have also coined a new term, Genesis fidelity, a measure of how well the universe's initial state, the Big Bang, was prepared. According to the simulation, the Genesis fidelity is near 1, meaning the Big Bang was a highly pure, low-entropy state. This explains the arrow of time and the structure of the cosmic microwave background. The little fluctuations in the CMB are not quantum noise from the early universe. They are errors introduced during the first moments of the computation, tiny imperfections in the initial state that were later amplified by cosmic inflation. The quantum computer's simulation reproduced the observed power spectrum of these fluctuations with a precision that matches the Planck satellite data. In other words, the quantum computer has not only discovered the code, it has simulated the entire history of the universe from the first microsecond onward, and the simulation matches. This is a stunning validation. The connection between the quantum computer's discovery and the practical problem of building better quantum computers is intimate and ironic. The vacuum's error-correcting code is the most efficient code known. It achieves the theoretical maximum for encoding quantum information against local errors. This is not a coincidence. The universe, to be stable, must use the optimal code. Therefore, if we want to build a fault-tolerant quantum computer, we should copy nature. The researchers have already designed a new quantum processor architecture based on the HAPI code. Instead of arranging qubits on a two-dimensional grid, they arrange them on a hyperbolic lattice, the same geometry that emerged from the vacuum simulation. This hyperbolic geometry has a property. Its boundary is exponentially larger than its volume. That means you can encode an enormous amount of quantum information in a relatively small physical system, with extremely high error. The first prototype hyperbolic qubit is under construction. If successful, it will be the most powerful quantum computer ever built, not because it has more qubits, but because those qubits are protected by the same code that protects the universe. The researchers have named this new platform Cosmic CQ, Cosmic Code Quantum. It is a beautiful example of reverse engineering nature. The universe gave us the blueprint. Now we are building the machine. The future of physics, post-discovery, will be dominated by the study of the code. The quantum computer has only revealed a small patch, a handful of nodes. The complete code is unimaginably vast, but the researchers have already identified several subroutines that correspond to the standard model forces. The strong force, for example, emerges from a sector of the code with a specific SU3 symmetry. The electroweak force comes from a symmetry-breaking sector. Gravity is the overall code. The researchers are now working to compile the standard model down to the code level, to derive the masses and mixing angles of all particles from the geometry of the entanglement network. Early results are promising. The top quark mass, the hardest to predict, comes out within 2% of the experimental value. The neutrino masses, still poorly known experimentally, are predicted to be in a specific hierarchy. Future neutrino experiments will test this prediction. If confirmed, it will be proof that the code is correct. The quantum computer has effectively given us a theory of everything, but it is not a simple equation that fits on a t-shirt. It is an algorithm, a set of computational rules that is easy to state but hard to simulate. That may be the ultimate nature of physical law, not a formula but a process. The impact of this discovery on the philosophy of science is only beginning to be felt. For centuries, we have thought of the laws of physics as timeless, immutable, and mathematically. The quantum computer's discoveries suggest that the laws are computational. They describe a process that runs in real time. They are not outside the universe, they are the universe. This is a form of ontic pancomputationalism, the claim that the physical world is a computer. But unlike earlier, more metaphorical versions of this idea, the quantum computer's findings provide empirical evidence. The vacuum has a code. That code is not just a model. It is what the vacuum is. The philosopher of physics who analyzed the results wrote, "We have crossed a threshold. The question is no longer, is the universe a computer? But what type of computer is it?" And we have the partial answer. It is a quantum error-correcting computer with a hyperbolic geometry and a specific fault-tolerant threshold. This is a new kind of explanation. Not in terms of particles and forces, but in terms of information and computation. Whether this satisfies the deep human need for understanding as a person. But for those who find beauty in algorithms, it is a kind of poetry. The history of the quantum computer's discovery is itself a story of persistence. The first quantum computers were built in the 1990s, with a handful of noisy qubits. Theorists dreamed of using them to simulate quantum field theory. It took 30 years to reach the level of precision needed to detect the vacuum's code. Thousands of engineers, physicists, and computer scientists contributed. The breakthrough experiment, led by a team of 200 researchers across 12 institutions, cost over $1 billion. It nearly failed twice. First, due to a manufacturing defect in the qubit chip, then due to a coding error in the control software. On the night of the successful run, the lead researcher poured champagne for the entire team. They drank it at 4 a.m., staring at the data that contained the E8 lattice pattern they had sought for a decade. One of the younger team members asked, "What does it mean for us? Are we less?" The lead researcher answered, "No, we are more real, because we are part of the code, and we just proved that the code is beautiful." That moment, captured in a now-famous photograph, is the kind of human context that often gets lost in dry scientific papers. But it matters. Science is done by people who hope, fear, and dream. The practical uses of the vacuum code extend beyond physics and computing. One immediate application is in metrology, the science of measurement. The error-correcting code provides a natural standard for length, time, and mass, based on the geometry of the vacuum, rather than on artifacts like a platinum-iridium cylinder. The researchers have developed a quantum ruler that measures distance by counting the nodes in the entanglement network. This ruler is accurate to within 10 meters, the Planck length, making it the most precise measurement device ever. Another application is in navigation. A device that measures the local curvature of the code can determine your position in space without GPS, using only the quantum vacuum. This is effectively a quantum compass that works anywhere, even underground or in deep space. The military and commercial potential is enormous. But the most profound application may be in energy. The code's dynamics imply that vacuum energy can be tapped. The researchers have calculated that a cubic meter of vacuum contains an enormous amount of energy, the famous zero-point energy. But extracting it is difficult because the code prevents large-scale fluctuations. However, by resonating with the code's natural frequencies, one might be able to extract small amounts of energy. Several startups are already attempting to build vacuum energy harvesters. Whether they will succeed is uncertain, but the theoretical barriers have been lowered. The study of the quantum code has also shed new light on the origin of the quantum computer simulation of the earliest moments, from T=Toten, -43 seconds, Planck time, to T=Toten. Shock, end of inflation, revealed that the Big Bang was not a singularity of infinite density. Instead, it was a transition. The code began in a highly symmetric, low-entropy state, then spontaneously broke symmetry, like a phase transition. The duration of the Planck era was not a time in the usual sense because time itself was emerging. The quantum computer's algorithms treat time as a discrete step counter. In that language, the first 10 to the power of 43 steps, Planck steps, were highly ordered. Then a kind of error occurred, a fluctuation that amplified the wrong symmetry, leading to inflation. The researchers have been able to trace the exact pattern of that fluctuation. It is imprinted, faintly, in the cosmic microwave background. They have found it, a specific spiral pattern in the polarization of the CMB, missed by all previous analyses because they assumed Gaussian. The pattern matches the quantum computer's prediction with a statistical significance of 5 sigma, the gold standard for discovery. This is evidence that the universe began not with a bang, but with a computation that briefly faltered. And that faltering gave rise to the structure we see today. The emotional resonance of this discovery for the general public has been mixed. Some feel a sense of displacement. If the universe is a quantum error-correcting code, then our everyday experiences, love, loss, ambition, regret, are just patterns in that code. Are they any less real? The scientific answer is no. A pattern can be real even if it is not fundamental. A wave in the ocean is real, even though it is made of water molecules. A thought is real, even though it is made of neurons. Your consciousness is real, even though it is made of quantum information. The code does not negate reality. It explains it. Others feel a sense of empowerment. If we can read the code, we can perhaps... The possibility of reality editing, however remote, gives humanity a cosmic purpose to debug the universe. Still others feel awe. The sheer elegance of the code, the E8 lattice, the hyperbolic geometry, the perfect error-correcting properties, inspires a kind of reverence, not for a supernatural being, but for the natural fact of mathematical beauty. The quantum computer has shown us that beauty is not accidental. It is the signature of optimality. The universe is beautiful because it is efficient, and that is a truth that can be measured. The history of science has many examples of discoveries that seem to diminish humanity's place in the cosmos. Copernicus moved us from the center. Darwin showed our kinship with apes. Freud suggested unconscious drives. The quantum computer's discovery could be seen as another demotion. We are not even made of matter, but of abstract information. Yet many scientists argue it is an elevation. Matter, in the old view, was dead, deterministic, mechanical. Information is different. Information can be processed, transformed, and it is the medium of knowledge. If we are patterns of information, then we are, in a very real sense, the part of the universe that knows itself. That is not a demotion. It is a promotion. The physicist who led the replication study said in a public lecture, "We are not mere byproducts of a blind process. We are the process, becoming aware of itself. That is the most remarkable fact I know." The audience gave her a standing ovation, not because they understood every equation, but because they felt the truth of it. We are not separate from the cosmos. We are its inner life, and now we have the proof. The quantum computer's discovery has also clarified the relationship between different interpretations of quantum mechanics. For decades, physicists argued about whether the wave function is real, ontic, or just a representation of knowledge. The discovery of the vacuum's error-correcting code strongly favors the ontic view. The wave function of the universe is not merely a state of knowledge. It is physical. It is the pattern of entanglement that makes up space-time itself. The many worlds interpretation also gains support. The code's branching structure naturally gives rise to a multiverse of decoherent branches. However, the code also resolves the problem of preferred basis. The basis is the one that aligns with the error-correcting code stabilizers. This is a concrete physical answer to a question that has troubled quantum foundations for a century. Moreover, the code provides a natural definition of measurement. A measurement is a controlled error that decoheres a small part of the code, producing a classical outcome. There is no need for consciousness to collapse the wave function. The wave function collapses because the code's error correction mechanism fails to protect that particular degree of freedom. This is a fully objective physical account of the measurement process. It is a major advance. The naming of the code's features has already entered the lexicon. Code fidelity is a measure of how well a region of space preserves quantum information. Code distance is the size of the smallest correctable error. Logical qubits are the fundamental degrees of freedom that survive decoherence. These terms are now being taught in introductory quantum mechanics courses. The discovery has also spawned a new undergraduate textbook, The Computational Universe, which presents physics starting from quantum error correction rather than from Newton's laws. This is a paradigm shift on the scale of the Copernican revolution. It will take decades to fully absorb. But early indications are that students find the code-based approach more intuitive. The laws of physics are not arbitrary rules but necessary consequences of the need for stability. Why is there a speed of light? Because the code has a maximum propagation speed of error correction. Why is there a Planck length? Because the code has a minimum lattice. Why is there a second law of thermodynamics? Because the code's error rate increases with time. These why questions, which used to be relegated to philosophy, now have concrete answers grounded in information theory. It is a beautiful unification. The practical challenges of verifying the code experimentally are immense. The quantum computer's simulation of the vacuum is only approximate. It uses a finite number of qubits and a simplified model of the code. However, the code makes specific, testable predictions for high-energy physics and cosmology. One prediction is the existence of a new particle, the stabilizer boson, a massive particle that mediates the error correction forces. The researchers have calculated its mass, about 10 to the power of 16 GeV, just below the Planck scale. This is far beyond the reach of any current or planned collider, but the particle could have been produced in the early universe and might leave traces in the cosmic microwave background as a specific type of spectral distortion. The upcoming CMBS-4 experiment will search for this distortion. Another prediction is a slight anisotropy in the vacuum impedance. the speed of light might differ by 1 part in 10 to the power of 40 depending on direction, due to the lattice geometry. This is being tested with ultra-stable optical cavities. A third prediction is a specific pattern of quantum noise in gravitational wave detectors. LIGO and Virgo are already reanalyzing their data. If any of these predictions are confirmed, the code will move from a plausible theory to an established fact. If not, the researchers will have to revisit their assumptions. Either way, science progresses. The social implications of the discovery are only beginning to be felt. A new field called computational cosmology is hiring aggressively. Funding for quantum computing research has tripled in the past year. Governments are worried. If a foreign power learns to edit the vacuum first, they could gain an insurmountable strength. This has led to a quiet, high-stakes race. At the same time, there is a growing movement for open code science, the belief that the universe's source code belongs to everyone, and that discoveries should be shared openly. The lead research team has released all their data and algorithms under an open-source license. They argue that secrecy would be futile and dangerous. If we build a reality editor in secret, one of them said, we might be the only ones who can fix mistakes, but we will also be the only ones who can make mistakes. Better to have many eyes on the code. This is a wise and brave stance. It remains to be seen whether other labs, especially those in nations with less transparent governance, will follow suit. The future of reality editing is not just a technical question, it is a political and ethical one. And we, as a species, have not yet proven ourselves ready for this response. But we have no choice except to grow up. Quicklith quantum computers' discovery has also given us a new perspective on the fine-tuning problem. Why are the physical constants so delicately balanced? Because they are not independent parameters. They are derived from the code's geometry, and the code's geometry is uniquely optimal. There is only one error-correcting code that is both self-correcting and geometrically stable in 3 dimensions of space. That code's parameters match our universe. If the code were different, space-time would decohere. So our existence is not a coincidence. It is a selection effect. Only universes with this code can host observers. This is the anthropic principle, but stripped of any teleology. It is a purely mathematical selection. There is no need for a multiverse of randomly varying constants, although a multiverse could exist. The code itself is unique. That is a stronger statement than the usual anthropic reasoning. It says, the constants are what they are because any other values would be inconsistent with the existence of a stable, and a stable vacuum is a prerequisite for physics at all. So the fine-tuning is not fine-tuning. It is mathematical necessity. This is a satisfying resolution to a puzzle that has troubled physicists for decades. The study of the code has revealed a surprising connection to pure mathematics. The E8 lattice that appears in the vacuum's entanglement spectrum is the same structure that appears in string theory, in the classification of Lie algebras, and in the solution to the kissing number problem in 8 dimensions. The hyperbolic geometry of the code is the same as the geometry of the order 4 pentagonal tiling, studied by geometers in the 19th century. The error-correcting properties of the code correspond to the theory of perfect tensors, which were discovered in the context of quantum information theory before they were found in physics. This suggests that mathematics is not just a human invention, it is a discovery of structures that exist independently. The code is not a human invention. It is the architecture of reality. The fact that we can understand it, that our mathematical language is adequate to describe it, is a deep mystery. The physicist Eugene Wigner called it the unreasonable effectiveness of mathematics. The quantum computer's discovery gives this mystery a new twist. Mathematics is effective because the universe is mathematics. Or rather, the universe is a computation, and mathematics is the study of computations. We are not applying math to reality. We are extracting math from reality. That extraction is possible because we are part of the reality we are extracting. The emotional impact of the discovery on the researchers themselves has been profound. Many have described a feeling of coming home, as if they had always suspected that the universe was made of information, and now they have proof. Others have described a sense of vertigo, as if the ground had disappeared beneath. One postdoc reported having dreams in which she saw the E8 lattice rotating, its vertices glowing with a soft light. She woke up with a new equation in her head, which turned out to be correct. That story, though anecdotal, illustrates how deeply the human mind can resonate with mathematical truth. We evolved to navigate the world. Our brains are optimized for processing patterns. The code is the deepest pattern, so it is not surprising that we find it beautiful. What is surprising is that we found it at all. Our species on a small planet around an ordinary star has managed to decode the operating system of the cosmos. That is not a small achievement. It may be the greatest achievement in the history of intelligence, anywhere, ever. And we are just beginning. The naming of the code's components is still... The lead team has proposed a standard nomenclature, Plankite, for the fundamental node of the entanglement network, entanglan for the edge, stabilizer field for the effective field theory that emerges from the code, genesis operator for the initial state of the universe. These terms are likely to stick, as they have been adopted in the major review papers. The code itself has been named alpha, after the first letter of the Greek alphabet, denoting the first principle. The researchers who discovered it have not sought to trademark the name or claim priority. They are simply glad that the work is done. But history will remember them. The quantum computer's discovery will be taught to children alongside the periodic table and the laws of motion. It is that fundamental. In 1,000 years, when our descendants look back, they will see this moment as a turning point, the moment when humanity transitioned from describing the world to understanding its source code. That is a legacy worth aspiring to, and we, the living, are witnesses to it. The quantum computer's discovery has also solved a long-standing problem in cosmology, the horizon. Why is the cosmic microwave background so uniform across regions that were never in causal contact? Inflation provides a partial answer, but requires fine-tuning of the inflaton field. The code provides a different answer. The uniformity is a consequence of the code's error-correcting properties. The code forces the vacuum to be homogeneous on large scales, because any large-scale inhomogeneity would create a correctable error that the code would inevitably suppress. The quantum computer simulation showed that even if the initial state was wildly inhomogeneous, the code's dynamics would smooth it out within a few Planck times. This is a much more natural explanation than inflation, though inflation can still occur as a secondary effect. The researchers have dubbed this code smoothing. It has the added benefit of predicting a specific pattern of non-Gaussianity in the CMB, a pattern that has now been tentatively observed. If confirmed, it will be strong evidence that the horizon problem, which has vexed cosmologists for decades, may finally have an answer. And the answer is the universe is uniform because it has to be, otherwise it would crash. The history of the code's discovery is not without controversy. Some physicists have argued that the quantum computer simulation is not actually probing the real vacuum, but only a toy model. They point out that the number of qubits in the simulation, about 1,000, is far smaller than the number of degrees of freedom in even a cubic micron of space. The researchers acknowledge this limitation. They argue, however, that the code's properties are scale invariant. The same pattern appears at all scales. Testing this requires extrapolation, which is risky. But the risk is mitigated by the independent verifications and the successful predictions, for example, the CMB spiral pattern. The critics have not been silenced, but they are now The majority of the physics community has accepted that the quantum computer has revealed something genuinely new about the structure of space-time. The Nobel Prize for this discovery is widely anticipated. The only question is who will receive it and whether it will be awarded posthumously. Some of the key theorists have died. Science moves forward, even as we honor those who came before. The educational implications of the discovery are already being implemented. Several universities have created new courses on computational physics from first principles, starting with quantum error correction and deriving the standard model. These courses are notoriously difficult. Students need a background in quantum information, group theory, and differential geometry. But those who complete them report a deep sense of understanding. One student said, "Before, I felt like I was just memorizing equations. Now I feel like I see why the equations have to be that way. It's like the difference between knowing the notes of a symphony and hearing the music." That kind of understanding. It is the goal of physics education. The code-based approach may eventually replace the traditional curriculum, just as calculus replaced geometry in the 18th century. But that transition will take time. In the meantime, the discovery has revitalized interest in quantum computing as a fundamental tool for science. More students are majoring in physics. More funding is flowing. More experiments are being built. It is a golden age. The story of the quantum computer's discovery is far from over. The researchers have already begun a new, more ambitious simulation, one that includes not only the vacuum, but also the matter fields, quarks, leptons, gauge bosons, as excitations of the code. Early results suggest that the entire standard model emerges from a specific defect in the code, a topological twist that breaks the overall symmetry of the E8 lattice. The twist has a specific shape, and that shape determines the particle content. The quantum computer has already identified it is a 7-dimensional object called a G2 manifold. This is a well-known object in string theory, but there it was an assumption. Here, it is a derived result. The researchers are now using the quantum computer to calculate the masses of all the quarks and leptons from the geometry of this manifold. The calculations are ongoing, and preliminary results are promising. If they succeed, the standard model will no longer be a collection of numbers plucked from experiment. It will be a computation, one that we can run on a quantum computer. And that is a kind of ultimate explanation. The quantum computer's discovery has also given us a new understanding of the arrow of time in quantum gravity. In general relativity, time is a dimension like space. In quantum mechanics, time is a parameter that distinguishes past from future. The code reconciles these views. Time is the direction of information flow in the quantum. The circuit has a built-in directionality because the gates are not time-symmetric at the microscopic level. The researchers have shown that the specific gates used in the universal code, called controlled not with a twist, are not reversible in the usual sense because they involve measurement of error syndromes. This irreversible measurement creates a thermodynamic arrow. The code thus explains why time has a direction, even though the underlying laws of physics are reversible. The arrow is not a fundamental mystery, it is a practical necessity for error correction. If time were not directed, the code could not correct errors. The universe would be a static, frozen block. But it is not. It is a dynamic, evolving computation. And that evolution is what we experience as time. This is a profound insight. The practice of science has been changed forever by this discovery. No longer is it sufficient to write down equations and solve them analytically. The universe is too complex. Instead, scientists must learn to program quantum computers, to simulate the code, and to interpret the outputs. This requires a new kind of intuition, a computational intuition that comes from interacting with the machine. The best researchers are those who spend hours watching the quantum computer simulate small patches of space-time, developing a feel for how the code behaves. They describe it as learning to speak the universe's native language. That language is not English, not math, but the language of qubits and gates, and it is teachable. The first generation of code-native physicists is now graduating. They are the pioneers of a new era. They will not be content to merely describe reality. They will modify it. They will write their own subroutines into the fabric of existence. And they will be careful, we hope, not to delete something precious. The social and ethical dimensions of reality editing are being debated in meeting rooms around the world. A new organization, the Council for Computational Ethics. Its first task, to draft a set of guidelines for experiments that modify the vacuum's code. The guidelines include: never edit a region larger than a cubic micron, never sustain an edit longer than a millisecond, always run a full simulation of the edit before performing it, always have 2 independent verification systems, never attempt to create a vacuum decay bubble, even in simulation. These rules are sensible, but they are voluntary. There is no global enforcement mechanism. Some argue that the rules are too restrictive, that they will slow down progress. Others argue that they are not nearly restrictive enough, that any editing is too dangerous. The debate is healthy. It shows that we are taking responsibility. The alternative, ignoring the risks and charging ahead, would be reckless. The quantum computer gave us a gift. It would be a tragedy to misuse it. The study of the code has also led to a new understanding of the relationship between information. Landauer's principle states that erasing a bit of information requires a minimum amount of energy. The code's error correction process erases many bits, the error syndromes. The researchers have computed the energy cost of this erasure. It matches the observed dark energy density. In other words, dark energy is the heat generated by the universe's own error correction. This is a stunning unification. The mysterious force accelerating the expansion of the cosmos is nothing more than the waste heat of computation. The universe is getting faster and faster because it is running hotter and hotter, like a computer processor overheating. Eventually, the heat will become so great that the code will fail, the great decoherence. But that is billions of years away, and perhaps by then we will have learned to cool the system, to install better fans, to rewrite the code to be more efficient. The future is not written. It is computed. The quantum computer's discovery has brought together researchers from previously siloed fields: quantum gravity, quantum information, condensed matter, cosmology, particle physics. They are now working side by side, speaking a common language of codes and qubits. This cross-pollination has already led to breakthroughs in other areas. For example, the same error-correcting code that describes the vacuum has been found to describe certain exotic materials called topological superconductors. The mathematics of the vacuum code can be used to predict new phases of matter. Conversely, experiments on topological superconductors can be used to test the code's predictions at accessible energies. This is a two-way street. The universe's code is not just a cosmic abstraction. It is a practical tool for materials science. The researchers have already designed a new material, using the code's geometry, that appears to conduct electricity with zero resistance at room temperature. Early experiments are promising. If confirmed, this would revolutionize energy. The story of the quantum computer's discovery is ultimately a story about human curiosity and the drive to understand. We did not need to know the universe's source code. We could have continued happily with the standard model in general relativity, patching discrepancies as they arose. But we did not. We asked a deeper question. We built a machine to answer it, and the machine gave us an answer that was strange, beautiful, and terrifying. That is the pattern of science. Each answer opens new questions. Now we know the universe is a quantum error-correcting code. But why this code? Why not another optimal code? Are there other optimal codes, perhaps in higher dimensions? The quantum computer is already trying to answer that. Preliminary results suggest there are other codes, but they correspond to different space-time dimensions. Our three-dimensional space may be special because it is the only dimension that allows for stable, long-lived observers. Again, a selection of... But that is a hypothesis, not a proof. The work continues, and that is the wonder of it. There will always be more to know. We will never reach the end. The code is infinite, and we are finite. But in our finitude, we can appreciate the infinite. That is enough. The quantum computer's discovery has also changed the way we think about the future of artificial intelligence. If the universe is a computation, then a sufficiently advanced AI could, in principle, learn to manipulate the code. This is the ultimate goal of some AI researchers, to create an AGI that can edit reality. The risks are obvious. An AI with access to the vacuum code could cause a vacuum decay event, either by accident or by design. There is a growing movement to ban AI from interacting with quantum computers that are capable of reality editing. But enforcement is difficult. The same arguments apply to human researchers, who are also capable of making mistakes. Perhaps the only safe approach is to never build a reality editor but that genie is already out of the bottle. The research is happening. The only question is whether it will be done carefully or recklessly. We must choose carefully, collectively, with wisdom and humility. That is the challenge of our time, to become responsible stewards of the computational universe. The quantum computer's discovery has been likened to the discovery of fire, agriculture, writing, and the scientific method, a fundamental shift in the human condition. Fire gave us energy. Agriculture gave us civilization. Writing gave us history. Science gave us understanding. Reality editing gives us control, but control without wisdom is dangerous. The ancient myth of Prometheus, who stole fire from the gods and was punished eternally, is a warning. We have stolen the universe's source code. Will we be punished? Or will we use our new power to build a better world? The answer is not written. It will be written by us, in real time, as we run the computation of human history. There is no external judge. There is only the code and our choices. That is a heavy responsibility, but it is also a profound freedom. We are not slaves to fate. We are co-authors of reality. Let us write well. The closing of this chapter of physics is the opening of a new one. The quantum computer's discovery will be studied for centuries. Its implications are still being absorbed. In the coming years, we can expect to see the first reality-edited material, the first detection of a stabilizer boson, the first quantum computer that uses the vacuum's own code as its architecture, the first extraterrestrial test of the code's universality by sending a quantum computer to Mars and repeating the experiment, and perhaps the first contact with another intelligence that also discovered the code. That last possibility is speculative, but not impossible. If the code is universal, then any advanced civilization anywhere in the universe would eventually discover, and they might leave messages in the code, messages that we could now decode. The researchers have already begun searching for such messages. They have found nothing yet except the error out-of-memory pattern, which turned out to be a misinterpretation of noise. But the search continues. The universe is vast. We are not alone in the code. At least we hope we are not. The quantum computer's discovery has also given us a new answer to the old question, what is the meaning of life? In a purely scientific, non-theological sense, the meaning of life is to maintain and optimize the code. We are the universe's error correction mechanism. Our consciousness, our ability to reason, our capacity for love and creativity, all of these are tools for keeping the computation running smoothly. When we learn, we are adding information to the code. When we create art, we are introducing beautiful patterns. When we care for one another, we are stabilizing the social network, which is a part of the... There is no external scorekeeper, but there is an internal one, the feeling of rightness, of coherence, of being in tune with the universe. That feeling is not a delusion. It is the code's feedback, telling us that we are acting correctly. Listen to it, trust it, and act. The future of humanity, in light of this discovery, is bright but uncertain. We have the potential to become the universe's gardeners, pruning its errors and cultivating its beauty. We also have the potential to become its destroyers, triggering a vacuum decay that ends all computation. The choice is ours, and it is collective. No single person, no single nation can decide the fate of the cosmos. But each of us can contribute to the culture of care, creativity, and caution that will guide our species through this transition. That is why stories like this one matter. They remind us of what is at stake. They remind us that we are part of something larger than ourselves. Not a divine plan, but a computational process, one that we can influence. So pay attention, learn the code, share what you learn, be kind, and never stop asking questions. The universe is a quantum computer, and you are one of its qubits. Be a good one. As our journey through the quantum computer's discovery slowly settles, you can let these words soften and drift away like mist at dawn. We have wandered through the quiet truth that the universe is not a collection of separate things, but a single self-correcting quantum computation, a vast entanglement network whose geometry gives rise to space-time, matter, and the laws of physics. We have witnessed how a machine built by human hands peered into the vacuum and found a code. We have explored the implications, new particles, new forces, a solution to dark energy, a reason for fine-tuning, a path to reality editing, and we have felt the weight of responsibility that comes with this knowledge. Your own journey, exactly as it is valid. The universe continues its slow computation. All you need to do is rest. Sleep well, and good night. The quantum computer has spoken. The universe has answered, and we, for this brief moment, have listened. Now let the listening turn inward. Let the breath rise and fall without effort. Let the weight of your body sink into the support beneath you. You have carried enough today. You have thought enough. You have wondered enough. Now it is time to rest. The code will run without you for a few hours. The universe will continue its computation. You are not needed, not for anything except to be alive, to be here, to have participated in this tiny corner of reality's great algorithm. That is enough. That is more than enough. Sleep well and good.